The men who built it said it could not be stopped. They were right. That was the problem. On the morning of February 11th, 1953, a Chesapeake and Ohio Class H-8 locomotive, engine number 1643, sat at the base of the Allegheny Grade in Hinton, West Virginia, coupled to a consist of 160 loaded coal hoppers stretching nearly 2 miles behind its tender. The combined weight of train and machine exceeded 18,000 tons. The temperature on the mountain had dropped to 4 degrees. The rails were sheeted in black ice no thicker than a playing card. The engineer that morning was a 51-year-old veteran named Howard Calhoun, who had run the Allegheny Grade for 19 years without a single serious incident. He had seen everything the mountain could produce: floods, blizzards, rock falls, collapsed tunnels. He placed his hand on the throttle and opened it with the same practiced confidence he had exercised 10,000 times before. What happened next was not supposed to be possible, because engine 1643 was not an ordinary locomotive. It was the largest, heaviest, most powerful steam engine ever built for regular service on an American railroad. 778,000 pounds of forged steel, copper pipe, and pressurized fire, producing 6,000 horsepower at the drawbar and pulling force that engineers at the Lima Locomotive Works had calculated carefully and with great pride would be sufficient to move a mountain. The men who designed it had called it the ultimate expression of steam power. A machine built at the precise moment when an entire nation's survival, its coal, its steel, its war production, its industrial heartbeat, depended on whether that coal could be dragged across the oldest mountain range on the continent. They had solved every engineering problem they could measure. Howard Calhoun knew this. He had ridden machines like 1643 for years. He trusted the numbers. He trusted the grade. He trusted the ice, because ice, at 4 degrees, behaves in a way that every textbook in Lima, Ohio said it should. The textbooks, it turned out, had not accounted for what happens when 18,000 tons begins to move backwards. Before there was a machine, there was the mountain. The Allegheny Range rises out of western Pennsylvania and eastern West Virginia with a geological indifference to human ambition that has not softened in 300 million years. It is not the tallest mountain system in North America. It is not the widest. But it is, by every measure that matters to a locomotive engineer, the most punishing. The grades are relentless, the curves are tight, the weather is unpredictable, and the tunnels, blasted through solid Appalachian bedrock by men with hand drills and black powder in the 1870s, were built for machines a quarter the size of what would eventually be asked to run through them. The Chesapeake and Ohio Railway had been fighting this mountain since 1873. The line had been chartered with a single commercial purpose: to move bituminous coal out of the interior coal fields of West Virginia and Kentucky to the tidewater ports of Hampton Roads, Virginia, from where it could be shipped to the steel mills and power stations of the industrial northeastern seaboard. The geography of this mission was straightforward on a map and brutal in execution. Between the coal fields and the coast stood the Allegheny Mountains, specifically the 17-mile climb from Hinton, West Virginia, up to Allegheny Summit, a vertical rise of more than 2,000 feet at grades that in some sections reached 1.5%. 1.5% sounds modest until you understand what it means in mechanical terms. For every locomotive pound of tractive effort generated at the wheel, a loaded coal train pushes back with the combined weight of its entire consist, pressed rearward by gravity, relentless, patient, and utterly without mercy. Early locomotives on the C&O grade were defeated routinely. Trains stalled mid-slope. Brakes failed on descents. Double-heading, coupling 2 locomotives together at the front of a train, became standard practice by 1890, and then triple-heading, and still the mountain won more arguments than it lost. In the first 3 decades of 20th century operations, the C&O spent more money, more man-hours, and more engineering thought on this 17-mile corridor than on any other segment of its entire 3,000-mile system. They widened cuts. They deepened drainage channels. They rebuilt the tunnels. The Big Bend Tunnel, already famous from the legend of John Henry, was eventually replaced entirely by a newer bore to accommodate wider equipment. They relayed the track with heavier rail. They installed centralized traffic control systems that at the time represented the most sophisticated railroad signaling in the world. And still the grade demanded more. By the mid-1930s, The arithmetic of the C&O's problem had become almost philosophical in its severity. American industrial demand for coal was accelerating. The coal fields of southern West Virginia were producing at volumes the original railway builders had never imagined. A single train of loaded hoppers could carry 6,000 to 8,000 tons of coal, but moving that train over the Allegheny summit required 3, sometimes 4 separate locomotives, each burning its own fuel, each demanding its own crew, each representing a capital cost and an operational liability. The bottleneck was not the coal fields. It was not the ports. It was 17 miles of mountain, and the C&O's president, Walter J. Touhy, understood by 1939 that if his railroad could not solve the grade problem would eventually solve his railroad. The solution he needed did not yet exist. Someone would have to build it. Lima, Ohio, in 1940, smelled of burnt iron and cutting oil and the particular sweet acrid scent of fresh foundry sand still hot from the pour. The city of 30,000 people in the flatlands of northwestern Ohio had one reason for its existence in the national industrial imagination, and that reason occupied 112 acres in its southeastern quarter, the Lima Locomotive Works. The company had been building steam locomotives since 1878, but its transformation into the dominant force in American motive power had begun in 1922, when a mechanical engineer named William Woodard introduced a design philosophy he called superpower. The concept was deceptively simple and revolutionary in execution. Maximize the steam generating capacity of the boiler, maximize the volume of steam admitted to the cylinders per stroke, and equip the locomotive with a sufficiently large firebox, supported by a trailing truck of 4 wheels rather than 2, to sustain that generation rate at high speed over long distances. Woodard's superpower locomotives did not merely pull harder than their predecessors. They pulled harder while moving faster while burning less coal per ton-mile of freight moved. The economics were transformative, and within 5 years of the first superpower locomotive's delivery, nearly every major American railroad had placed orders with Lima. The works at its peak employed 3,800 men across 3 primary production buildings: the erecting hall, where the largest components were assembled, the machine shop, which ran 24 hours in wartime, and the foundry, which produced castings weighing up to 70,000 pounds in a single pour. The erecting hall was a cathedral of industrial purpose, 900 feet long, roofed in corrugated steel that amplified every sound to a physical sensation, its floor occupied at any given moment by a dozen locomotives in various stages of assembly, each one in the process of becoming something that would outlive the men who built it by decades. Overhead cranes moved on steel rails bolted to the roof trusses, carrying boilers and cylinders, and driving wheel sets weighing tons, maneuvering them with a precision that seemed improbable given the scale. The men who worked in the erecting hall were not interchangeable. The boilermakers who sealed the firebox sheets with copper stays driven by hand hammers had learned their trade through apprenticeships lasting 4 years. The machinists who fitted the valve gear, the intricate network of rods, eccentrics, and reversing levers that controlled the timing and direction of steam admission to the cylinders, worked to tolerances of 1,000th of an inch on components that would operate in temperatures above 700 degrees Fahrenheit for decades without adjustment. When a Lima-built locomotive failed in service, the failure was almost never traced back to the erecting hall. The men in that building took a proprietary pride in their work that was not commercial sentiment. It was professional identity. A locomotive they had built was going somewhere. It was going to do something. Weakness was not permitted. In 1939, the C&O sent its chief mechanical officer, a methodical Virginia engineer named George Fowler, to Lima with a set of requirements that the company's own design engineers privately considered at the outer boundary of what steam technology could deliver. Fowler wanted a locomotive that could haul 160 loaded hoppers, approximately 11,000 tons of train, over the Allegheny grade unassisted. No helper locomotives. No double heading. 1 engine, 1 crew, 1 trip. He wanted it to sustain this performance in conditions ranging from midsummer heat to midwinter ice. He wanted a machine that could be maintained by the existing workforce at the C&O's Hinton shops without specialized tooling. And he wanted it to fit within the C&O's existing loading gauge, the dimensional envelope defined by tunnel clearances and bridge ratings that had been built for equipment one-third its intended size. Lima's chief engineer, Herbert Snyder, listened to Fowler's requirements, asked 3 questions, and then was silent for what witnesses later recalled as an uncomfortably long time. Then he picked up a pencil and began to draw. The first problem Herbert Snyder drew a line through was geometry. The CNO's tunnel clearances allowed a maximum locomotive height of 16 feet, 2 inches from rail to the top of the stack. The boiler diameter required to generate steam at the rate Fowler's performance targets demanded was, by straightforward thermodynamic calculation, 108 inches. 108 inches of cylindrical steel boiler, plus the thickness of lagging insulation, plus the smoke box at the front, plus the cab at the rear, had to fit beneath 194 inches of vertical clearance while sitting atop driving wheels that themselves stood 67 inches tall, 4 inches more than any previous CNO locomotive. Because larger driving wheels were thermodynamically necessary to convert the available steam pressure into the tractive force Fowler required without destroying the valve gear through mechanical stress. Snyder's solution was to lower the boiler's centerline by dropping the firebox between the rear driving axles rather than above them, a configuration enabled by the trailing truck design Woodard had pioneered in 1922, but taken to a scale Woodard had never attempted. The firebox that resulted was not merely large. It was, at the time of its design in 1940, the largest firebox ever fitted to a steam locomotive in regular service in North America, 135 inches long, 96 inches wide, with a grade area of 135 square feet. A man could stand upright inside an empty firebox of this design. In service, burning Appalachian bituminous coal at maximum rate, it consumed approximately 100,000 pounds of coal per day, roughly the output of a small underground mine. The second problem was tractive effort. Fowler's requirement for unassisted tonnage over the grade translated, in engineering terms, to a starting tractive effort of not less than 110,000 pounds at the drawbar. Achieving this figure required cylinder dimensions, diameter, and stroke that would generate forces on the main driving rods that exceeded the yield strength of any connecting rod material then in standard production use. Snyder's team spent 4 months on this problem alone, ultimately specifying a proprietary steel alloy for the main rods and specifying a manufacturing process that included X-ray inspection of every finished rod, a quality control procedure borrowed from aircraft engine production that had never previously been applied to steam locomotive components. The connecting rods that emerged from this process were 14 feet long, 6 inches in diameter at the center, and weighed 1,200 pounds each. They were, by a significant margin, the most precisely engineered reciprocating components ever installed in a steam locomotive. The third problem was weight. The sum of boiler, cylinders, firebox, running gear, and cab produced a locomotive weight, without tinder, of 778,500 pounds. This was distributed across 4 sets of driving wheels arranged in 2 groups of 4 axles each, a wheel arrangement designated in American practice as 2-6-6-6, indicating 2 leading wheels, 6 coupled drivers on the front engine, 6 coupled drivers on the rear engine, and 6 trailing wheels. The resulting axle loadings were precisely within the CNO's track capacity, but the margin was narrow. Snyder's team calculated that any single design decision adding more than 1,200 pounds to the locomotive's weight would require the CNO to rebuild sections of its main line track before the locomotive could enter service. Every subsequent design iteration was conducted with a weight ledger open on the drafting table, every component's mass tracked to the pound. The fourth problem had no engineering solution. It was a problem of imagination. No one had ever operated a locomotive of this size. There was no operational data, no failure history, no maintenance record, no body of experience to draw from. The men in Lima's design office were working from first principles applied at a scale beyond any precedent, using mathematics they trusted and metallurgy they had tested to predict the behavior of a machine that did not yet exist in a service environment they could only approximate. When Snyder submitted the final drawings to the CNO in November 1940, the specification package ran to 4,200 individual engineering drawings. The locomotive had been designed on paper to a level of detail that accounted for thermal expansion of the boiler under operating pressure, the dynamic imbalance forces generated by the reciprocating rods at maximum speed, and the stress concentration at every significant weld joint in the boiler shell. What the drawings could not account for was the mountain's patience. The Allegheny grade had been wearing machines down for 60 years. It had done so quietly, methodically, and without the slightest acknowledgement of engineering confidence. The blueprints said the new locomotive would be sufficient. The mountain, as always, was waiting to form its own opinion. The C&O placed its initial order in December 1940, 8 locomotives, to be delivered by September 1941. Lima accepted. The erecting hall was cleared. The foundry began its first heats. The Titan was about to be born. The first casting for Locomotive 1600 was poured on January 14, 1941, at 6:22 in the morning. The foundry foreman that day was a 44-year-old Czech immigrant named Emil Dvorak, who had worked Lima's floor since 1919 and who kept a personal logbook of every significant pour he had supervised: date, heat temperature, alloy composition, ambient humidity, any anomaly in the metal's behavior as it entered the mold. His logbook entry for January 14th was 3 sentences long and entirely without sentiment. First H-8 bed casting. 68,400 pounds. Clean pull. What those 3 sentences represented in human terms was 2 weeks of mold preparation by a crew of 14, 6 days of furnace preheating, and a pour that required every overhead crane in the foundry operating simultaneously to manage the ladles of molten steel in the correct sequence without allowing temperature loss that would compromise the crystalline structure of the finished casting. The bed casting, the locomotive's frame, the structural spine to which every other component would eventually be bolted, welded, or pressed, had to absorb, without permanent deformation, the combined shock loading of 2 sets of reciprocating cylinders firing 240 times per minute at steam pressures of 260 pounds per square inch, across a service life projected at 30 years and 2 million miles. It had to do this in temperatures ranging from -20 degrees Fahrenheit on a West Virginia mountain in February to 140 degrees inside a cab in an Ohio summer. It had to do it while carrying 778,500 pounds of locomotive weight on 6 driving axles, on track whose alignment was never perfect and whose joints transmitted a continuous percussion of micro-impacts up through the wheels and into the frame at every mile of every run. Dvorak's clean pull notation meant the casting had emerged from its mold without voids, cracks, or cold shuts, defects that in a component of this structural criticality would have required scrapping the entire casting and beginning again. It had taken 3 previous attempts on a scaled test casting to achieve a clean pull on the bed design. Each failure had cost the project 11 days and approximately $4,000 in materials. The successful pour on January 14th meant that Locomotive 1600, the first of what would eventually become a class of 60 machines, could proceed to the machine shop, where the rough casting would spend the next 6 weeks undercutting tools, removing 2,400 pounds of excess metal and producing the finished bore dimensions and mounting surfaces to which all subsequent assembly work would be held. The erecting hall received the first machined frame in early March. Over the following weeks, components arrived from across the Lima campus and from outside suppliers. Boiler sections from a fabricator in Pittsburgh, driving wheel sets forged in a facility in Akron, the massive cast steel cylinders from Lima's own foundry, the superheater elements, thin steel tubes coiled inside the boiler flues to elevate steam temperature from 400 to 750 degrees before it reached the cylinders, assembled by hand by a crew of 6 boilermakers who worked in 4-hour shifts. Because the heat inside the boiler barrel made longer exposure medically inadvisable, the men in the erecting hall worked 6 days a week, 10 hours a day. Assembly of a single H-8 required approximately 45,000 man-hours of direct labor. At the wage rates of 1941, averaging 94 cents per hour for skilled trades, the labor cost per locomotive was roughly $42,000, against a total unit cost to the C&O of approximately $270,000. The men who drove the overhead cranes, who fitted the valve gear, who drove the 4,200 copper boiler stays with hand hammers, and then caulked every seam against leakage at operating pressure, earned wages that their families remembered as good wages for that time, in that place, in an economy that had only recently stopped collapsing. Locomotive 1600 was rolled out of the erecting hall on August 23, 1941, 15 days ahead of the contracted delivery date. A company photographer recorded the moment. In the photograph, Emil Dvorak stands at the far left edge of the frame, partially cut off, his logbook under his arm. He is not looking at the camera. He is looking at the locomotive. His expression is unreadable. The CNO moved Locomotive 1600 to Hinton, West Virginia, by September 3, 1941. The town of Hinton sat in a narrow river valley at the foot of the Allegheny Grade, its existence organized almost entirely around the railroad, the shops, the yard, the turntable, the coaling tower that rose above the town's roofline like an industrial campanile. The arrival of a new locomotive in Hinton was not, ordinarily, an occasion for ceremony. Locomotives came and went. Men inspected them, fueled them, watered them, and sent them up the mountain. But 1600 attracted a crowd. Word had circulated through the shops and the yard offices and the boarding houses along the tracks. Something different was coming. Something large. Large was an insufficient word. The H-8 stood 16 feet, 2 inches to the top of the stack. It stretched 125 feet from the front pilot to the rear of the tender. Standing beside its driving wheels, 67 inches in diameter, their rims worn to a mirror finish from the final grinding process at Lima. A grown man's eye level reached only to the wheel's center. The machine did not look like a development of previous technology. It looked like a different category of object. Several of the older shop workers in Hinton, men who had spent 30 years maintaining CNO power, walked its length in silence and said nothing when they reached the end. The initial test runs were conducted without revenue tonnage. On September 8th, 1600 made its first unloaded ascent of the grade, pulling only its tender and a single measurement car instrumented to record drawbar pull, boiler pressure, steam temperature, cylinder cutoff, and will slip. The assigned engineer was a 38-year-old company man named Robert Ashby, selected for his familiarity with articulated locomotives. The H-8's 2-6-6-6 wheel arrangement made it technically an articulated compound design, with the front and rear engine assemblies capable of independent lateral movement through curves. Ashby had run the CNO's previous largest power, the H-7 class, for 4 years. He reported afterward that 1600 felt, on first application of the throttle, like nothing he had previously experienced. The acceleration was not dramatic in terms of speed. It was dramatic in terms of sensation. The feeling, he wrote in his test report, of forces being applied that are simply larger than anything the track seems prepared to accept. The first loaded test came on September 19th. It consists of 120 loaded hoppers, approximately 8,400 tons of coal and car, was assembled in the Hinton yard. Under the observation of George Fowler, Herbert Snyder, and 3 CNO officers, Ashby opened 1600's throttle at 7:14 a.m. The train moved. It moved without hesitation, without wheel slip, without the labored exhaust bark of a locomotive working at its limit. It moved the way a machine moves when it has margin left over. Fowler's notes from that morning record, with characteristic engineering restraint, that the locomotive performed within predicted parameters on initial grade entry. What his notes do not record is that 2 of the CNO officers watching from the grade's observation point subsequently shook hands, something that men of their professional culture did not do lightly. The mountain, however, offered its first response 4 weeks later. On October 15th, a 140 hopper consist behind Locomotive 1601, the second H-8 delivered, encountered a section of rail that maintenance crews had reported as marginal but had not yet replaced. At 22 miles per hour on the upper grade, the locomotive's front engine truck encountered a joint separation that deflected the leading axle laterally by approximately 3/4 of an inch. At that speed, with that weight, 3/4 of an inch was sufficient to initiate a lateral oscillation, a hunting motion, in the front engine assembly that propagated rearward through the locomotive's frame and produced, over the next 200 feet of track, a series of rail impacts that spiked to loads the track structure had not been designed to absorb. No derailment occurred. But 11 rail spikes were sheared from their ties, and a 40-foot section of track required immediate replacement before the line could reopen. The incident cost the C&O 6 hours of service, a crew of 12 men working through the night, and the quiet acknowledgement, recorded in an internal memorandum from Fowler's office, that the H-8 and the Mountain had not yet reached a full understanding of each other. That understanding would take time. It would exact a price. On December 8, 1941, the day after Pearl Harbor, the C&O's general traffic manager sent a single-page internal directive to every yard office on the system. It contained no rhetorical flourish and required no interpretation. It stated that effective immediately, all freight priority classifications were suspended, all passenger freight scheduling conflicts were to be resolved in favor of freight, and all motive power was to be operated at maximum sustainable capacity until further notice. The directive did not specify how long further notice might extend. It did not need to. The H-8 was about to meet the war it had, without knowing it, been built for. The arithmetic of American wartime coal demand was staggering in its scale. Steel production, the foundation of every weapon, ship, vehicle, and piece of ordnance the war required, consumed approximately 650 million tons of coal between 1942 and 1945. Naval fuel oil, while supplanting coal for ship propulsion, still required coal-fired power for its refinery processing. The electric power stations that ran the aluminum smelters for aircraft production, the munitions factories, the shipyards, and the military training bases ran almost entirely on bituminous coal. And the largest, most accessible, most productive coal region in the eastern United States lay in the southern West Virginia and eastern Kentucky coalfields served by the Chesapeake and Ohio Railway, whose coal reached the industrial Northeast through a single primary corridor, up the Allegheny Grade, through the mountains, and out to Tidewater. The C&O moved 72 million tons of coal in 1942. It moved 81 million tons in 1943. It moved 88 million tons in 1944. These numbers represented a volume of commerce that the railroad's physical infrastructure had not been designed to handle, that no American railroad had ever been asked to handle, and the H-8 fleet, expanded by 1943 to 25 locomotives operating on the Hinton to Clifton Forge corridor, was the mechanism by which the impossible numbers became possible. The locomotives ran on schedules that their designers at Lima had calculated as sustainable but had never tested at sustained duration. A typical H-8 in wartime service made 2 complete round trips over the grade per day, 4 mountain crossings, each consuming between 50 and 55 tons of coal and 15,000 gallons of water. The tenders behind the locomotives held 25 tons of coal and 25,000 gallons of water, requiring resupply at both ends of each run. The water supply infrastructure at Hinton and Clifton Forge, the track pans, the water columns, the treatment plants that softened the mineral-laden mountain water to prevent boiler scale, operated without shutdown for 38 consecutive months between June 1942 and August 1945. When components failed, they were repaired in place, by whatever means were available, without taking the system offline. There was no option of offline. The Hinton shops ran 3 shifts, 7 days a week, through the entire war. The workforce, depleted by military service to approximately 60% of its pre-war strength, absorbed the remaining 40% labor hours through mandatory overtime that averaged 62 hours per week. The men who performed the running maintenance on the H-8s, the boiler washouts, the valve setting checks, the driving box lubrication, the brake rigging inspections, did so on turnaround times that pre-war standards would have considered dangerously compressed. A locomotive that under peacetime scheduling would have received a full mechanical inspection every 30 days was inspected every 21 days. A boiler washout that required 18 hours was completed in 14. These compressions were not reckless. They were calibrated. The shop foreman understood exactly what margin they were consuming and why, and they consumed it with the specific knowledge that the coal moving over the mountain behind their machines was feeding furnaces that were building ships that were keeping men alive in waters 5,000 miles away. 2 H-8s suffered boiler failures during wartime operations. Both occurred on the grade. The first, in March 1943, was a flue tube failure that vented superheated steam into the cab and burned the firemen. a 24-year-old from Alderson, West Virginia, named Curtis Webb, on his left arm and shoulder. Webb returned to service 6 weeks later. The second failure, in November 1944, cracked a stay bolt in the firebox crown sheet of Locomotive 1611, releasing a jet of steam that extinguished the fire before pressure could build to catastrophic levels. The locomotive was stopped, the crew was uninjured, and 1611 was back in service 11 days later. That both failures were contained rather than catastrophic was not luck. It was the consequence of Snyder's engineering conservatism and Dvorak's foundry standards applied 18 months earlier in Lima, Ohio. The mountain continued to exact its toll in other ways. 3 derailments occurred on the grade during wartime, all caused by track failures under loads that exceeded the structure's original design parameters. In each case, the H-8 remained upright, its weight distribution and low center of gravity working in its favor even as the track beneath it gave way. The coal it was carrying did not reach its destination on schedule, but the locomotive came home. By August 1945, the 60 locomotives of the H-8 class, a second order of 35 having been placed with Lima in 1942 and a third order of 5 following in 1944, had moved, collectively, approximately 400 million tons of freight over the Allegheny Grade. The war ended. The coal kept moving. The mountains had not won. Not yet. The cab of an H-8 Allegheny in full service was not a workspace. It was a furnace with instruments. The firebox door sat 18 inches behind the engineer's left shoulder. When the fireman opened it to add coal, an action performed every 40 to 90 seconds at maximum output. The radiant heat from the interior, burning at temperatures above 2,400 degrees Fahrenheit, struck the back of the cab like a physical blow. In summer, cab temperatures during the grade climb regularly exceeded 140 degrees Fahrenheit at head height. In winter, the same firebox that cooked the men on their left side left their right sides exposed to outside air admitted through the cab's open right window, because the engineer required an unobstructed view of the right-of-way, and the window could not be closed without eliminating that sight line. The resulting thermal environment, one side of the human body at 140 degrees, the other at whatever the Allegheny winter chose to produce, was not something that training fully prepared a man for. It was something he either learned to endure or he did not. The men who endured it were a specific type. CNO engineer culture in the 1940s was hierarchical, technically demanding, and almost entirely oral in its transmission of critical knowledge. A man hired as a fireman, the entry-level cab position, responsible for maintaining boiler pressure through precise fuel management, spent an average of 7 years on that side of the cab before being promoted to engineer. During those 7 years, he learned not from manuals, but from the engineer he worked beside, absorbing through proximity and repetition the specific knowledge of how a particular locomotive on a particular grade behaved under particular conditions. He learned that Locomotive 1607 ran slightly hot on the front cylinder head and required the lubricator to be backed off by half a turn on the upper grade. He learned that the reverse curve at milepost 34 required the throttle to be eased 2 notches before entry, or the rear engine assembly would haunt. He learned that the particular sound of a wheel slip on the upper grade, a brief, high-pitched screech that lasted less than a second before the sanding system suppressed it, meant the rail conditions had changed and the throttle setting that had been adequate for the last 2 miles was no longer adequate for the next 2. None of this knowledge was written down. All of it was essential. The fireman's physical demands were separate from the engineer's and no less severe. A round trip over the Allegheny Grade consumed between 100 and 110 tons of coal fed into the firebox by the automatic stoker, a mechanical device driven by a small steam turbine that augmented, but did not replace, the fireman's manual management of fire distribution across a 135-square-foot grate. The stoker delivered coal to the grate center. The corners and rear edges required hand firing. On a full output climb, the fireman threw coal by hand every 30 to 60 seconds, using a 10-pound scoop, bent at the knees in the confined cab space, opening the firebox door against the blast of heat, placing the coal with precision rather than merely throwing it, because coal dumped on an already hot section of grate would cause uneven combustion that reduced steam pressure exactly when the grade demanded maximum pressure. A fireman working a full shift on the H-8 lifted, by conservative calculation, between 3 and 4 tons of coal by hand during a single round trip. The engineers who ran the machines were, almost without exception, men who had come up through this physical apprenticeship and who carried in their bodies the accumulated memory of the grade. They knew it in their hands on the throttle, and their ears tuned to exhaust rhythm, and their eyes reading the track ahead for the subtle surface changes, a dull sheen of moisture, a slight darkening of color, that indicated rail conditions changing faster than any instrument could report. They were not romantic figures. They were skilled industrial workers doing an extraordinarily demanding job for wages that reflected its dangers incompletely. Howard Calhoun, who would sit at the throttle of Locomotive 1643 on the morning of February 11, 1953, had fired and engineered on the Allegheny grade for 23 years. He had trained under an engineer named Pershing Wills, who had trained under a man whose name is no longer recorded. The knowledge Calhoun carried that February morning was 3 generations deep. It was not deep enough. The temperature at Hinton, West Virginia, at 5 a.m. on February 11, 1953, was 4 degrees Fahrenheit. The previous 48 hours had produced an alternating sequence of light precipitation and partial clearing that meteorologists would later identify as the specific atmospheric condition most dangerous to mountain railroad operations. Temperatures oscillating near freezing, producing a cycle of melt and refreeze that coated rail surfaces not with the visible white frost that crews could identify and respond to, but with a transparent film of bonded ice, black ice, that was indistinguishable from dry rail under artificial lighting and had a coefficient of friction between steel wheel and steel rail that reduced adhesion by approximately 65% below the dry rail values on which locomotive performance calculations were based. Howard Calhoun completed his pre-departure inspection of Locomotive 1643 at 6:40 a.m. His fireman, a 31-year-old named Gerald Pickett, had the fire built to pressure, 260 pounds per square inch, the H-8's operating maximum, by 7 o'clock. The sanding system, which released dry sand from gravity-fed boxes onto the rail ahead of the driving wheels to improve adhesion in exactly the conditions that morning presented, was tested and confirmed functional. The train, 160 loaded hoppers, 11,200 tons of coal, 2¼ miles of coupled cars, had been inspected by the yard crew. All air brakes had been tested. All couplings had been verified. Calhoun departed Hinton Yard at 7:23 a.m., 12 minutes behind schedule due to a coupling adjustment on the rear of the consist. The first 6 miles of the grade were unremarkable. 1643 performed within normal parameters. Its exhaust a steady, rhythmic percussion that the men in the Hinton yards could hear for 15 minutes after departure, a sound that was, to that community, as ordinary and as reliable as weather. Calhoun held his throttle setting at 65% and monitored his steam pressure, which held steady at 255 pounds. Pickett managed the fire with the automatic stoker supplemented by periodic hand firing of the rear grate corners. The speedometer read 18 miles per hour, which was the standard service speed for the upper grade. At milepost 9, the rail conditions changed. The precise sequence of events in the following 4 minutes was reconstructed afterward from Calhoun's statement, Pickett's statement, the locomotive's performance recorder, a device that inscribed a continuous paper tape with speed, throttle position, and brake cylinder pressure, and the physical evidence left on the track. At milepost 9, the gradient increased from 0.9% to 1.4%. The combination of increased grade and the black ice that coated this section of track, which faced northeast and had not received direct sunlight since the previous autumn, reduced wheel adhesion below the threshold at which 1,643's driving wheels could maintain forward movement against the combined weight of the consist pressing rearward down the hill. The wheels began to slip. Slipping wheels on a steam locomotive produce a distinctive auditory signature, a sudden rise in exhaust frequency and pitch as the wheels spin freely rather than rolling under load, that an experienced engineer can identify and respond to in under 2 seconds. Calhoun identified it. His response was textbook: close the throttle, activate the sanders, allow wheel speed to reduce toward rail speed, then reopen the throttle gradually. The response took 1.8 seconds from slip onset to throttle closure. Under dry rail conditions, this response would have been more than adequate. Under the conditions of February 11th, the sanders discharged their sand onto ice that was too smooth and too cold for the granules to embed. The sand spread laterally and was carried off the rail surface by the slipstream of the passing wheels. The driving wheels, decelerated by throttle closure, did not find adhesion. They found less ice, and then more ice, and then, at the moment their rotational velocity fell below the velocity of the train, still moving forward from momentum, they locked. Locked wheels on a locomotive decelerating on a 1.4% downgrade, behind 11,200 tons of loaded coal cars whose own brakes had not yet been applied, produced a force equation with one solution. The train began to move backwards. In the first seconds, the rearward movement was almost imperceptible, less than 1 mile per hour, the consist's momentum barely overcoming its static inertia downhill. Calhoun released the locomotive brakes to prevent wheel flat spotting and applied the train line brakes, the air brakes controlling the entire consist, in a graduated application designed to bring the train to a controlled stop. The air brakes on the leading cars responded within their normal parameters. The air brakes on cars 80 through 160, the rear half of the consist, 2 miles behind the locomotive, responded more slowly, as the brake signal propagated rearward through the train line at the speed of compressed air, which is not, at 2 miles, instantaneous. In the interval between the leading cars slowing and the trailing cars continuing to push, the consist compressed forward, a phenomenon called a run-in, and the slack between couplings closed along the length of the train in a chain reaction that reached locomotive 1643 as a single longitudinal impact load estimated afterward at 340,000 pounds. The locomotive moved backward 6 feet in under 1 second. What followed was 11 minutes of controlled crisis that demonstrated, simultaneously, the limits of the machine and the competence of the man operating it. Calhoun managed the brake application with a precision that, under the circumstances, bordered on the implausible, modulating train line pressure to prevent the locked rear cars from jackknifing on the curved section of grade below milepost 8, maintaining enough forward brake force to slow the rearward movement without inducing a derailment from brake-locked wheels dragging laterally across curved rail. Pickett maintained boiler pressure throughout, understanding without instruction that his engineer would need full steam the moment adhesion could be recovered. The train came to rest at milepost 7.6, 1.5 miles below its high point, after descending under imperfect control for 11 minutes at speeds that reached a maximum of 7 miles per hour. No derailment occurred. No cars were damaged beyond coupler wear. No member of the crew was injured. When the CNO track supervisor arrived by truck from Hinton, he found Howard Calhoun standing beside locomotive 1643 on the track, his hand on the front pilot, looking up the grade. He was not speaking. He did not speak for several minutes. What he said, when he finally did, was not recorded. Between 1941 and 1956, the 60 locomotives of the CNO H-8 class moved approximately 900 million tons of freight over the Allegheny grade. 900 million tons. The number resists ordinary comprehension. Expressed in physical terms, it represents roughly 90 million loaded coal hoppers. A single train of that length would encircle the Earth at the equator 7 times. Expressed in economic terms, it represents the raw material foundation of an industrial output that included steel for 10 million automobiles, aluminum for 40,000 aircraft, coal for the power stations that lit every city on the eastern seaboard for 15 years. Expressed in human terms, it represents something harder to quantify, but no less real. The economic sustenance of the coalfield communities of West Virginia and Kentucky, whose men went underground every morning and whose families ate because a machine in the mountains was strong enough to carry what the mines produced to the places that needed it. The land through which the H-8 carried this commerce paid a price that the ledgers of the Chesapeake and Ohio Railway did not record. The 17 miles of the Allegheny grade sat above a watershed that fed the Greenbrier River and, through it, the New River and eventually the Kanawha. Waterways that the communities of the New River Gorge and the Greenbrier Valley depended on for water supply, fishing, and the modest agricultural economy that existed alongside the coal industry. The coal dust that fell from 160 hopper trains at speeds of 18 to 22 miles per hour was not trivial in volume. Studies conducted in the late 1940s by the West Virginia Department of Natural Resources estimated that a single loaded H-8 consists shed between 800 and 1,400 pounds of coal dust per trip over the grade, deposited along the right-of-way and carried by rain into the adjacent watershed. 60 locomotives making 2 round trips daily produced a deposition rate that, over 15 years, altered the sediment chemistry of tributary streams for distances of up to 4 miles from the track bed. The human communities along the corridor absorbed other costs. Hinton's population peaked at approximately 6,800 in 1944, sustained almost entirely by the railroad's wartime employment. The noise environment of a town through which 60-plus heavy freight trains passed daily, each one preceded by the locomotive's whistle at every grade crossing, each one accompanied by the concussive exhaust of an H-8 working at full output, was not, by any available measurement standard of that era, compatible with normal residential life. Residents who had lived in Hinton for decades reported, in oral histories collected by West Virginia University in the 1970s, that they had ceased to consciously register the sound of the locomotive's passing. It had become, they said, simply the sound of the air, the sound of existing in that place and time. What the locomotives gave, they gave without apology and on a scale that transformed the region. The Hinton shops, at peak wartime employment, provided jobs to 1,400 workers, approximately 1 in 4 of the town's adult males. The wages those workers earned circulated through a local economy of boarding houses, hardware stores, pharmacies, diners, and churches that existed in their particular form because the railroad existed. The schools that children attended in Hinton in 1944 were funded by property tax revenues generated in large part by the C&O's assessed valuation. The tracks, the shops, the coaling towers, the locomotives themselves, each one assessed for local tax purposes at approximately $200,000, a sum that in a small West Virginia county represented significant public revenue. The paradox of the H-8's commercial legacy was not unique to this machine or this railroad. It was the central paradox of American industrial development in the 20th century, that the same mechanism which sustained communities also deformed them, that the economic vitality generated by industrial scale was inseparable from the environmental and human costs that scale imposed, that the men who drove the locomotives and the men who maintained them and the women who kept the households running on their wages all participated, willingly and necessarily, in a system whose full accounting they were not given the means to perform. Howard Calhoun returned to the Allegheny grade 3 days after the February incident. He made 64 more round trips over the mountain before his retirement in September 1954. He never spoke publicly about the morning of February 11th. His personnel file at the C&O, reviewed by a railroad historian in 1987, contained a single notation about the incident: train handled within operational parameters. No damage. Crew performance satisfactory. Satisfactory, a word that contained, in its bureaucratic compression, 11 minutes of a man managing the consequences of forces larger than any single human decision could have prevented or predicted. The mountain kept no records, but it remembered everything. The first Electromotive Division F7 diesel locomotive arrived on the C&O system in 1950. It weighed 230,000 pounds. It produced 1,500 horsepower. It required no fire, no boiler washout, no water supply infrastructure, no coal tower. It needed no warm-up period in cold weather. Its fuel, diesel oil stored in a saddle tank beneath the car body, did not blow from an open hopper at 20 miles per hour and coat the right-of-way in combustible particulate. A single mechanic with a set of hand tools could perform its weekly maintenance in 8 hours. Against the H-8 Allegheny, it was laughably underpowered. One F7 produced barely a quarter of one H-8's output. But 4 F7s lashed together in multiple unit operation, controlled by a single engineer from the lead cab, produced 6,000 horsepower at a combined operational cost per ton-mile that was, by the C&O's own accounting, 34% lower than the H-8's. The economics were not close. They were not a matter of interpretation or institutional preference. They were an arithmetic fact, and the men who ran the Chesapeake and Ohio Railway in 1950 were not sentimental about arithmetic. The transition had been building since 1945. General Motors' Electromotive division had spent the war years refining its diesel technology under the sustained demand of military contracts, and by 1946, it was offering railroads a product that had moved decisively beyond the experimental phase it had occupied in the late 1930s. The diesel did not simply replace steam power. It made steam power's entire supporting infrastructure, the water treatment plants, the coal towers, the ash pits, the specialized boilermaker workforce, the complex valve setting protocols, not merely unnecessary, but a liability. Every dollar invested in maintaining that infrastructure was a dollar that could not be recovered because the infrastructure itself was becoming worthless. The C&O's management understood this. They had understood it by 1948, when an internal study commissioned by the railroad's operating department projected that complete dieselization of the main line could be achieved by 1957 at a capital cost that would be recovered through operating savings within 6 years. The study did not address what would happen to the men whose expertise was specific to steam, the boilermakers, the valve setters, the engineers whose 20 years of grade knowledge was encoded in the behavior of a technology that was being discontinued. Those men were not in the study's accounting. Their knowledge was not on the balance sheet. On the Allegheny grade itself, the transition was technically demanding in ways that the diesel's proponents had initially underestimated. The grade's ruling resistance, the precise combination of gradient, curvature, and distance that defined the minimum tractive effort required to move a given tonnage, had been engineered around by the H-8's specific performance characteristics. The diesel's tractive effort curve was different in shape from the steam locomotives. It produced its maximum pulling force at very low speed and saw that force decline as speed increased, while the H-8 produced its maximum output at a moderate speed and sustained it across a broader range. For the heavy, slow coal drags that were the Allegheny grade's primary traffic, the diesel's torque characteristics were actually well suited. The problem was not performance. The problem was transition. The last H-8 built, Locomotive 1659, completed at Lima in 1948, entered service in a railroad that was already planning for its obsolescence. By 1952, the C&O had dieselized its passenger operations entirely. By 1954, diesel units were handling a growing percentage of the coal drag operations. By the end of 1956, the H-8s were being removed from service systematically, their boilers tested a final time, their valve gear marked with chalk annotations indicating the wear dimensions that a future overhaul, an overhaul that would never come, was required to address. Lima Locomotive Works, the company that had built them, ceased locomotive production in 1951. The erecting hall where Emile Dvorak had watched Locomotive 1600 roll into daylight was converted to diesel engine assembly and then, within a decade, to other industrial uses. The specific knowledge that had existed in that building, in the hands of the boilermakers, the machinists, the foundry workers, dispersed into retirement, into retraining, into the general silence that follows the end of a particular kind of making. The last H-8 in regular revenue service on the C&O made its final run over the Allegheny grade on April 14, 1956. No record survives of who the engineer was. Of the 60 H-8 Allegheny locomotives built between 1941 and 1948, 58 were scrapped. The scrapping was efficient and without ceremony, conducted at railroad-owned facilities in Huntington, West Virginia, and Covington, Virginia, over a period of approximately 18 months between late 1956 and early 1958. A locomotive that had cost $270,000 to build, approximately $3.1 million in 2024 dollars, was recovered as approximately 385,000 pounds of scrap steel, generating a return of perhaps $7,700 at prevailing scrap prices. The economic ratio of construction to destruction was roughly 35-1. The men who cut them apart worked with acetylene torches, starting at the cab and working forward, the boilers deflated and cold, the fireboxes dark for the first time in 15 years. 2 locomotives survived. Locomotive 1601, the second H-8 ever completed, the machine that had sheared 11 rail spikes in October 1941 on its first encounter with the mountain's indifference, was acquired by the Baltimore and Ohio Railroad Museum in Baltimore, Maryland, where it has been preserved in static display since 1961. It stands in the museum's roundhouse among other artifacts of American railroad history, its 67-inch driving wheels resting on a short section of preserved track, its boiler cold, and its firebox empty. Visitors who stand beside it in the roundhouse and place their hands on its driving wheel rim are touching metal that was poured in Emile Dvorak's foundry on a January morning in 1941, that was fitted by men whose names are mostly lost, that was driven up the Allegheny grade by men whose knowledge has gone with them. The wheel does not transmit this history. It is simply cold and very large. Locomotive 1604 resides at the Henry Ford Museum in Dearborn, Michigan, where it has been displayed since 1966. It is considered by railroad historians to be the better preserved of the two survivors, its external finish more complete and its documentation more extensive. It was donated to the museum by the C&O with a package of engineering drawings, maintenance records, and operational data that constitutes one of the more complete archives of a single-steam locomotive type in American preservation. Scholars who have worked with that archive report that the engineering drawings alone, the 4,200 sheets produced in Herbert Snyder's drafting office in 1940, represent a level of documented technical ambition that remains impressive by any contemporary standard. Howard Calhoun retired from the C&O in September 1954, 14 months before the last H-8 ran the grade. He lived in Hinton until his death in 1971. In a house on a street that ran parallel to the main line, close enough that he could hear the diesels passing in the night, a sound entirely unlike the sound he had spent 23 years producing and interpreting. Whether he registered the difference consciously, or whether the sound of the air in Hinton had simply changed and he had changed with it, is not recorded. His obituary in the Hinton Daily News noted his years of railroad service and his membership in the Brotherhood of Locomotive Engineers. It did not mention February 11, 1953. The Allegheny grade still exists. The track is still active. Coal still moves over it, though in volumes reduced from the wartime peak and in cars pulled by modern diesel-electric units that their crews operate from air-conditioned cabs equipped with GPS positioning systems, electronic air brake controls, and digital performance recorders that would have seemed not merely advanced but incomprehensible to Gerald Pickett hand-firing the rear grate corners of Locomotive 1643 at 4 degrees Fahrenheit in the dark of a February morning. The mountain has not changed. It is the same 17 miles, the same 2,000 feet of vertical rise, the same northeast-facing curve at milepost 9, where the sun does not reach in winter and the ice forms in the specific, particular way that ice has always formed there, transparent and patient and indifferent to the confidence of the machines that cross it. It is waiting, as it has always waited, for the next machine that believes it cannot be stopped. Every machine, eventually, can be stopped. The mountain knows this. It has always known this. The Titans came and pulled their impossible weights and filled the nation's furnaces and then went cold and silent under the acetylene torch, and the mountain remained. Older than coal, older than iron, older than the human need to move things from one place to another across the face of an indifferent earth. The steam is gone. The grade remains.